Good evening, everyone, and welcome to your favorite sleep channel, The Droning Professor. Tonight, we're going to learn about the multiverse hypothesis, so as you make yourselves comfortable, please take a moment to let us know where you're listening from and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. I hope you're all comfortable because tonight we're going to take a journey that makes Frodo's trek to Mordor look like a trip to the corner store. We're going to talk about the multiverse, which is essentially the idea that our universe, this impossibly vast expanse containing billions of galaxies, each with billions of stars, might just be one universe among countless others. I know what you're thinking. Professor, I can barely handle keeping track of one universe. I still haven't watched all the Marvel movies. But stick with me, because this is going to be one wild ride through physics, philosophy, and the kind of mathematics that makes your brain feel like it's doing gymnastics. Let me start by saying that when I first encountered the multiverse hypothesis as a graduate student back in the 1990s, I thought my advisor had been inhaling too much lab chemical fumes. Multiple universes? It sounded like bad science fiction. But here's the thing about physics. Sometimes the universe, or should I say universes, are stranger than any fiction we could dream up. The multiverse isn't just some wild speculation cooked up by physicists who had too much coffee. It actually emerges naturally from several of our best theories about how reality works. And that's either really exciting or really disturbing, depending on whether you've had your existential crisis this week yet. So what exactly is the multiverse? At its core, the multiverse hypothesis suggests that our observable universe, everything we can see with our most powerful telescopes, everything from the cosmic microwave background radiation to the most distant galaxies, is just one bubble in a much larger cosmic foam. Imagine blowing soap bubbles as a kid. Each bubble is a complete universe unto itself, with its own physical laws, its own constants of nature, maybe even its own versions of you sitting in a classroom somewhere wondering if there are multiple universes. Some versions of you are probably paying better attention right now. Good for them. Now, before we dive deeper, I need to address something important. The multiverse is not a single theory. It's more like a buffet of different theoretical frameworks, each suggesting multiple universes for different reasons. Some of these frameworks overlap, some contradict each other, and some are so speculative that even theoretical physicists look at them sideways. But they all share one thing in common. They challenge our notion that what we see is all there is, and that's philosophically uncomfortable for a lot of people. It was uncomfortable for me. It might be uncomfortable for you. That's okay. Science is supposed to make us uncomfortable sometimes. Let's start with what I consider the most respectable version of the multiverse hypothesis, the one that comes from cosmic inflation. Back in 1980, a physicist named Alan Guth proposed the theory of cosmic inflation to solve some nagging problems with the Big Bang theory. The Big Bang was great, don't get me wrong, but it left some questions unanswered. Why is the universe so uniform when we look at it on large scales? Why is space so flat? These sound like weird questions, but they bothered cosmologists. Guth's solution was elegant and, frankly, bonkers. He proposed that in the first fraction of a second after the Big Bang, specifically between about 10 to the negative 36th seconds and 10 to the negative 32nd seconds after the universe began, space underwent exponential expansion. And when I say exponential, I mean the universe doubled in size again and again and again in the tiniest fractions of time you can imagine. During this inflationary period, a region smaller than a proton expanded to something much larger than our entire observable universe today. It's like if you had a grape and suddenly it became larger than the Milky Way galaxy in less time than it takes light to cross an atom. Your brain is probably protesting right now, and that's a perfectly reasonable response. But here's where it gets interesting for our discussion tonight. In the most popular models of inflation, this process doesn't just happen once and then politely stop. Instead, inflation is eternal. Once inflation starts, it keeps going in most regions of space. But in some regions, it stops, and those regions become universes like ours. Meanwhile, the inflating regions keep expanding exponentially, and occasionally new regions stop inflating and form new universes. This process continues forever, creating an infinite number of bubble universes, each with potentially different physical properties. This is called eternal inflation, and it was developed further by physicists like Andrei Linde and Alexander Vilenkin in the 1980s. Think of it like a pot of boiling water. The whole pot is the eternally inflating space, and the bubbles that form are individual universes. Each bubble is causally disconnected from the others, meaning nothing in one universe can ever influence or communicate with another universe. You could never visit these other universes, never send them a postcard, never even know they're there through any direct observation. They're beyond what physicists call our cosmological horizon. And before you ask, no, this doesn't violate the principle that theories should be testable. We'll get to that thorny issue later. But wait, there's more. And this is where things get really strange. In an infinite multiverse of this type, if something can happen, it will happen. Not just once, but infinitely many times. This isn't mysticism. It's just statistics applied to infinity. If there are infinite universes and a finite number of ways particles can be arranged, then every possible arrangement must occur infinitely many times. That means somewhere out there, if eternal inflation is correct, there's a universe exactly like ours, except you sneezed one extra time when you were 7 years old. There's a universe where the Roman Empire never fell. There's a universe where I'm not standing here giving this lesson, but instead became a professional accordion player. The mind reels. Now, let's shift gears and talk about quantum mechanics. Because if inflation gives us one type of multiverse, quantum mechanics potentially gives us another, and this one is even stranger, which I know seems impossible at this point. You've probably heard of Schrödinger's cat. That poor hypothetical feline that's both alive and dead until you open the box. This is a thought experiment designed to illustrate the strangeness of quantum superposition, the idea that quantum systems exist in multiple states simultaneously until they're measured. The traditional interpretation of quantum mechanics, called the Copenhagen interpretation, says that when you measure a quantum system, its wave function collapses. Before measurement, an electron can be in a superposition of multiple locations. After measurement, it's in one definite location. The wave function, which describes all the possible states the system could be in, suddenly collapses to one outcome. It's like the universe is playing with a deck of cards and only shows you one card when you look, even though before you looked, all the cards were somehow in play simultaneously. But here's the problem. Why does measurement cause collapse? What counts as a measurement? These questions bothered a graduate student named Hugh Everett back in 1957. His solution, which initially seemed crazy and was largely ignored for years, was radical. What if the wave function never collapses? What if, instead, every time a quantum measurement happens, the universe splits into multiple branches, one for each possible outcome? In one branch, the electron is measured here. In another branch, it's measured there. Both branches are equally real, and both continue to exist. This is the many worlds interpretation of quantum mechanics, and it suggests that reality is constantly branching into countless parallel universes with every quantum event. And remember, quantum events happen constantly, everywhere, at every scale. Particles decay, atoms interact, photons are absorbed. Each event, according to many worlds, spawns new universes. The number of universes in this interpretation is staggeringly large and growing exponentially with every passing moment. Right now, as I speak, the universe is splitting into countless branches. In some of them, you're still paying attention. In others, you've fallen asleep. In still others, you never came to class today. The many worlds interpretation solves some problems in quantum mechanics. It's deterministic, meaning the wave function evolves according to precise mathematical laws without any mysterious collapse. It doesn't require an observer to cause something magical to happen. But it comes at a cost, and that cost is accepting that an unfathomable number of parallel universes exist, most of which we can never interact with or observe. Critics argue this violates Occam's razor, the principle that we shouldn't multiply entities beyond necessity. Supporters counter that many worlds is actually simpler because it doesn't require adding a collapse mechanism to the theory. Both sides have been arguing about this since the 1970s, and they'll probably still be arguing about it when we're all retired. Let's talk about another source of multiverses, one that comes from string theory. Now, I know string theory has a reputation. It's been called everything from the most promising theory of everything to an untestable mathematical fantasy. The truth is probably somewhere in between. String theory attempts to unify quantum mechanics and general relativity by proposing that the fundamental constituents of reality aren't point particles but tiny vibrating strings. Different vibrations of these strings correspond to different particles. An electron is one vibration pattern, a quark is another, a photon is yet another. It's like the universe is a cosmic symphony, and particles are different notes. But string theory has a problem, and it's a big one. For the mathematics to work consistently, string theory requires extra dimensions of space beyond the three we're familiar with. Depending on which version of string theory you're working with, you need 9 or 10 spatial dimensions. That's right. We might be living in a universe with 9 or 10 dimensions of space and 1 of time, but we only perceive 3 of space because the others are curled up so small we can't detect them. Imagine a garden hose. From far away, it looks one-dimensional, just a line. But if you're an ant walking on it, you'd discover it also has a circular dimension curled around. String theory proposes something similar happens with the extra dimensions, except they're curled up at scales far smaller than anything we can currently probe. Here's where the multiverse comes in. The way these extra dimensions curl up is called compactification, and there are many, many ways it can happen. Estimates suggest there might be 10 to the power of 500 different possible configurations, a number so large it has its own name, the string theory landscape. Each different configuration would give rise to a universe with different physical laws, different particle masses, different force strengths. Some configurations might produce universes where atoms can't form. Others might have physics wildly different from ours. And if eternal inflation is also true, then each of these possible configurations might be realized somewhere in the eternally inflating multiverse. We don't just have multiple universes. We have multiple universes with different laws of physics. This leads to what's called the landscape multiverse, and it's controversial even among string theorists. Some see it as a bug, a sign that string theory doesn't really predict anything if it predicts everything. Others see it as a feature, a way to explain why our universe has the particular physical constants it does through something called the anthropic principle. I'll get to that shortly because it deserves its own discussion and probably its own therapy session. Before we go further, I want to mention a few other types of multiverses that have been proposed, just so you have a complete taxonomy. There's the mathematical universe hypothesis, proposed by physicist Max Tegmark, which suggests that every mathematically consistent structure exists as a physical universe. This is wild because it means not just universes with different physical constants, but universes with entirely different mathematical laws underlying reality. Tegmark categorizes multiverses into 4 levels. Level 1 is just distant regions of our own universe beyond our horizon. Level 2 is the inflationary multiverse with different physical constants. Level 3 is the many worlds quantum multiverse. And level 4 is the mathematical multiverse where different mathematical structures exist as physical realities. Then there's the simulation hypothesis, which isn't exactly a multiverse theory but often gets grouped with them. This is the idea that our universe might be a computer simulation created by some advanced civilization. If that's true, then presumably the simulators could run multiple simulations, giving us a multiverse of simulated universes. This idea has gotten a lot of attention in popular culture, partly because Elon Musk won't stop talking about it, but it has serious proponents in philosophy and physics. The argument goes that if it's possible to create realistic simulations of universes, and if civilizations typically create many such simulations, then statistically speaking, we're probably in a simulation rather than base reality. Sleep well tonight with that thought. Now, let's address the elephant in the room, or perhaps I should say the infinite number of elephants in infinite rooms. How do we test the multiverse hypothesis? This is the criticism that makes many scientists uncomfortable with the whole idea. Science is supposed to be based on testable predictions. You propose a theory, make predictions, and then do experiments or observations to check if the predictions are correct. If your theory can't be tested, it's not science, it's philosophy or, worse, speculation. And the multiverse seems fundamentally untestable because, by definition, other universes are beyond our ability to observe. But defenders of the multiverse hypothesis argue that the situation isn't quite so hopeless. First, they point out that we don't test theories directly. We test predictions that follow from theories. And some multiverse theories do make testable predictions about our universe. For example, eternal inflation makes predictions about the distribution of temperature fluctuations in the cosmic microwave background radiation. We can test those predictions, and so far, they've held up reasonably well, though alternative theories can explain the data too. Second, some argue that the multiverse is a prediction of theories we've already tested, not a theory itself. We didn't invent eternal inflation because we wanted a multiverse. We discovered that eternal inflation, which was proposed to explain observations about our universe, naturally leads to a multiverse. String theory was developed to unify quantum mechanics and gravity, not to produce a landscape of universes. If our best theories predict a multiverse as a consequence, should we ignore that prediction just because it's difficult to test directly? That seems unscientific too. Third, there might be indirect ways to detect other universes. If our bubble universe collided with another bubble universe in the past, it might have left a mark in the cosmic microwave background, a kind of cosmic bruise. Researchers have looked for such signatures and haven't found convincing evidence yet, but the search continues. Similarly, if we ever develop a complete theory of quantum gravity that uniquely predicts a multiverse, and if that theory makes many other testable predictions that turn out to be correct, that might give us indirect confidence in the multiverse prediction, even if we can't test it directly. But I'll be honest with you, this is contentious. Many physicists think the multiverse is unfalsifiable and therefore unscientific. Others think it's a legitimate scientific hypothesis that we're just not yet technologically advanced enough to fully test. The debate has been going on since the 1980s and shows no signs of resolution. Welcome to the frontiers of physics, where we argue about what counts as science. Let's talk about the anthropic principle, because this is where the multiverse hypothesis intersects with one of the deepest questions we can ask. Why is the universe the way it is? Our universe appears to be fine-tuned for life. The strength of gravity, the mass of the electron, the charge of the proton, the cosmological constant, dozens of physical parameters seem to have values that fall within narrow ranges, that allow for the existence of complex structures like atoms, molecules, stars, planets, and ultimately life. Change any of these values by even a small amount, and you'd get a universe where stars can't form, or where they burn out too quickly, or where atoms are unstable, or any number of other scenarios incompatible with life as we know it. This apparent fine-tuning demands an explanation. One possibility is that there's some deeper theory we haven't discovered yet that uniquely predicts these values. That would be elegant and satisfying. Another possibility is that there's an intelligent designer who chose these values specifically to allow life. That's a theological answer that science can't address. But a third possibility is the anthropic principle combined with the multiverse. If there are many universes with different physical constants, then, of course, we find ourselves in one of the rare universes where the constants allow life, because we couldn't exist in the others. We observe a fine-tuned universe not because all universes are fine-tuned, but because observation requires observers, and observers require a special kind of universe. This is called the weak anthropic principle, and it's really just selection bias applied to cosmology. The strong anthropic principle goes further and suggests the universe must have properties that allow life to develop, but that's more controversial and gets into teleological territory that makes scientists nervous. The weak version is more palatable. We observe what we observe because we're here to observe it. The anthropic explanation is unsatisfying to many scientists because it seems to give up on finding a fundamental explanation for physical constants. Instead of asking, why is the electron mass what it is, we're answering because if it weren't, we wouldn't be here to ask. That feels like a cop-out. But defenders argue that in an infinite multiverse, the anthropic principle might be the only possible explanation for some features of our universe. Not everything needs a deeper cause if the landscape of possibilities is vast enough. Let me give you a concrete example. The cosmological constant, which determines the rate at which the universe's expansion is accelerating, has a value of about 10 to the negative 123 in Planck units. Theoretical calculations suggest it should be much larger, about 10 to the positive 123 times larger. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in physics. If the cosmological constant were much larger, galaxies and stars never would have formed because space would have expanded too rapidly. Without galaxies and stars, no life. In a landscape multiverse where different universes have different values of the cosmological constant, we necessarily find ourselves in a universe where it's small enough for structures to form. This anthropic argument was actually made by physicist Steven Weinberg in 1987, before we even knew observationally that the cosmological constant was non-zero. He used anthropic reasoning to predict a range of values, and when astronomers discovered dark energy in 1998, the observed value fell within Weinberg's predicted range. That's either a stunning success for anthropic reasoning or a lucky coincidence, depending on who you ask. Now I want to address some philosophical implications because the multiverse, if true, fundamentally changes how we think about reality, probability, and even ethics. Let's start with probability. In a finite universe, probability makes sense. If you flip a coin, there's a 50% chance it comes up heads. But in an infinite multiverse, where all possible outcomes occur, how do we make sense of probability? There are infinitely many universes where the coin came up heads, and infinitely many where it came up tails. Infinity equals infinity. What does probability even mean in that context? This is called the measure problem in cosmology, and it's a genuine technical challenge. To make predictions in an infinite multiverse, you need to define a measure, a way of weighing different regions or outcomes to assign probabilities. Different measures can give radically different predictions, and there's no consensus on which measure is correct or even if a unique correct measure exists. Some cosmologists think this is a fatal problem for eternal inflation. Others think it's a technical challenge we'll eventually solve. Then there's the Boltzmann brain problem, which is delightfully weird. Ludwig Boltzmann was a 19th century physicist who worked on statistical mechanics. One implication of his work is that in an infinite universe with infinite time, random thermal fluctuations could spontaneously create any structure, including a brain complete with memories indistinguishable from your brain right now. These are called Boltzmann brains, and in some models of eternal inflation or universes with infinite lifetimes, there should be far more Boltzmann brains than evolved brains like ours. If that's true, you should assume you're probably a Boltzmann brain, a momentary fluctuation in a vast void, and all your memories are false. That means you can't trust your observations or reasoning, which means you can't trust the theory that led to this conclusion, which creates a logical paradox. Physicists take this seriously because any theory that predicts you're probably a disembodied brain spontaneously forming in empty space is probably wrong. Theories need to be adjusted to avoid predicting that we're Boltzmann brains, which constrains which multiverse models are viable. What about ethics and meaning in a multiverse? Some people find the multiverse nihilistic. If every choice you make spawns a universe where you made the opposite choice, do your choices matter? If there are infinite versions of you making every possible decision, what's the significance of this particular version's choices? This is sometimes called quantum immortality in the many worlds interpretation. In some branches, you survive that risky decision. In others, you don't. But there's always a branch where you continue to exist, so from your subjective perspective, you never experience your own death. Does that mean you should take absurd risks? I certainly hope not, but I think this concern is misplaced. Even if infinite copies of you exist, your choices still determine the experiences of this particular copy in this particular branch of reality. Your decisions still cause joy or suffering, success or failure, in this world, which is the only one you directly experience. The existence of other versions of you making different choices doesn't make your choices meaningless any more than the existence of other people making different choices makes your choices meaningless. Each branch of reality, each universe, contains real experiences and real consequences. The multiverse doesn't give you a moral excuse to abdicate responsibility. Let's talk about some of the scientific critics of the multiverse hypothesis. Not all scientists who reject the multiverse are motivated by philosophy or religion. Many have concrete scientific objections. Some argue that eternal inflation hasn't been definitively proven and might not be the correct explanation for our universe's properties. Others point out that string theory, despite decades of work, hasn't yet made a single unique, testable prediction. If a theory can explain anything, it explains nothing. The landscape problem might not be a feature, but a sign that we're on the wrong track entirely. Physicist Paul Steinhardt, who was one of the early developers of inflation theory, has become a critic of eternal inflation, arguing that it makes the theory unfalsifiable and therefore unscientific. Physicist Lee Smolin has argued against the anthropic principle and landscape multiverse, suggesting instead that universes might reproduce through black holes, with physical constants evolving through a kind of cosmological natural selection. Philosopher of science Karl Popper emphasized falsifiability as the demarcation criterion for science, and by that standard, some multiverse proposals might not qualify as scientific theories at all. But other philosophers and physicists respond that Popper's falsifiability criterion is too strict and doesn't capture how science actually works. Many successful scientific theories make predictions that are difficult or impossible to test directly. We believe in quarks not because we've observed individual quarks, they can't exist in isolation, but because the theory of quarks makes many other testable predictions that have been confirmed. Similarly, we might come to accept the multiverse, not through direct observation, but through the success of theories that predict it. Let me describe some of the empirical evidence that does exist, weak as it may be. The cosmic microwave background radiation, that relic heat from the early universe, shows patterns that are consistent with inflation theory. The temperature fluctuations we observe match predictions from quantum fluctuations stretched to cosmic scales during inflation. This doesn't prove eternal inflation, but it supports inflation generally, and eternal inflation is a natural consequence of most inflation models. So we have indirect evidence. In 2010 and 2011, some researchers claim to have found evidence of bubble collisions in the cosmic microwave background, circular patterns that could be bruises from our universe colliding with other bubble universes. These claims were controversial and haven't been confirmed by other analyses. Most cosmologists think these patterns are probably just statistical flukes or artifacts of the analysis method. But the fact that researchers are actively looking for such signatures shows that the multiverse isn't completely beyond empirical investigation. Quantum mechanics experiments continue to produce results consistent with the predictions of the many worlds interpretation, though they're also consistent with other interpretations. An experiment would need to somehow distinguish between interpretations, which is extraordinarily difficult. Some theoretical proposals exist for how we might do this, involving careful manipulation of quantum systems to see if the other branches have any subtle effects. But these experiments are well beyond our current capabilities and might be impossible in principle. From string theory, researchers continue to work on understanding the landscape and whether there might be regions of the landscape that produce our observed physics uniquely or with high probability. If they could show that most of the landscape produces universes like ours, that would be evidence against needing anthropic reasoning. Conversely, if our universe's properties are typical of the small fraction of the landscape that supports observers, that would support the anthropic multiverse picture. This work is ongoing and involves complex mathematics that I'm mercifully not going to put you through tonight. I want to mention some variations and related ideas that blur the lines between science, philosophy, and speculation. There's the simulation argument I mentioned earlier, which philosopher Bostrom formalized in 2003. He argues that at least one of three propositions must be true. Civilizations never reach the technological capability to create realistic simulations. Civilizations that reach that capability choose not to run such simulations, or we are almost certainly living in a simulation. The logic is probabilistic. If simulations are possible and common, then simulated beings vastly outnumber real beings, so you're probably simulated. This isn't strictly a multiverse theory, but it suggests multiple levels of reality, which is conceptually similar. There's also the idea of modal realism from philosopher David Lewis, which holds that all possible worlds are as real as the actual world. In this view, when we talk about possibility, we're talking about things that actually happen in other equally real worlds. This is a metaphysical position rather than a physical theory, but it shares the multiverse's commitment to taking possibilities seriously as real entities. Some physicists have explored whether conscious observation plays a role in creating the universe, an idea that connects to quantum mechanics and the observer effect. The participatory anthropic principle, proposed by physicist John Wheeler, suggests that observers are necessary to bring the universe into being. In some interpretations, this could mean consciousness plays a role in determining which branch of the quantum multiverse we experience. This is highly speculative and most physicists don't take it literally, but Wheeler was a respected physicist who worked with Niels Bohr and contributed significantly to general relativity and quantum mechanics, so the idea has pedigree even if it remains fringe. Let me bring this back to something more concrete. What would it mean for our daily lives if the multiverse exists? Honestly, probably nothing. If other universes are beyond our ability to access or observe, they don't affect us any more than events outside our cosmological horizon affect us. We can't visit them, can't communicate with them, can't trade with them or be invaded by them. The multiverse, if real, is the ultimate example of something that exists but doesn't interact with us in any way. It's metaphysically important but practically irrelevant. That said, ideas have consequences. If the multiverse became widely accepted scientifically, it would change how we think about our place in reality. We'd go from being in the universe to being in a universe, a small part of a much vaster structure. That's happened before in history. Copernicus showed we're not at the center of the solar system. Hubble showed our galaxy is one of billions. Each step made us cosmically less special. The multiverse is the next step in that progression. Some find that humbling and awe-inspiring. Others find it depressing or meaningless. I think it's whatever you make of it, which is true of most scientific discoveries. The multiverse also affects how we think about fundamental physics. If we accept that some properties of our universe are anthropically selected from a landscape of possibilities rather than uniquely determined by fundamental laws, that changes what we look for in a theory of everything. It means a complete theory might explain why some things are possible, but not why this particular possibility is realized. That would be a shift in what we consider a satisfactory scientific explanation, and not everyone is comfortable with that shift. Let's address one more objection I often hear. Isn't the multiverse just giving up? If we can't explain why our universe has the properties it does, we invent infinite other universes with different properties and say, see, no explanation needed, it's just selection bias. Isn't that lazy? I understand this concern. Science progresses by finding deeper explanations, not by multiplying entities. But I'd argue that the multiverse hypothesis, at least in its respectable forms, isn't invented to explain away fine-tuning. It's a prediction of theories that were developed for other reasons. Inflation was developed to solve the flatness and horizon problems. String theory was developed to unify quantum mechanics and gravity. The many worlds interpretation was developed to avoid the measurement problem in quantum mechanics. The multiverse falls out of these theories, whether we want it or not. That said, we should be cautious. The history of science includes many examples of entities that were proposed but don't exist, from the luminiferous ether to phlogiston to Vulcan, the hypothetical planet inside Mercury's orbit. Just because a theory predicts something doesn't mean that something is real. The theory might be wrong or incomplete, so healthy skepticism is warranted. But dismissing the multiverse hypothesis entirely because it's counterintuitive or unfalsifiable seems premature. Many of our best confirmed theories started out seeming absurd. I want to close by putting this in historical perspective. Every time humans have developed better tools to observe reality, we've discovered that reality is larger and stranger than we thought. Ancient humans thought the world was the land they could walk across. Early astronomers thought the universe was the solar system. Then we discovered our galaxy. Then we discovered billions of galaxies. Then we discovered the universe is expanding and had a beginning. Each discovery revealed a vaster cosmos. The multiverse is simply the next step in that progression, the proposal that the totality of reality might be vastly larger than even our huge observable universe. Whether the multiverse exists is an open question. We don't know, and we might never know for certain. But the fact that our best theories lead us to consider the possibility seriously tells us something important. We don't fully understand the nature of reality yet. We have excellent theories that describe aspects of reality with incredible precision. General relativity and quantum mechanics are two of the most successful scientific theories ever devised. But they don't fit together, and when we try to combine them or extend them, we get strange predictions like multiple universes. Maybe those predictions are correct. Maybe they're signs that we're missing something fundamental. But either way, we're still in the process of figuring things out, which is exactly where science should be. The multiverse hypothesis reminds us to stay humble about our understanding and open to radical possibilities. It also reminds us that the universe doesn't care about our preferences or intuitions. Reality is under no obligation to make sense to us or to be the way we'd like it to be. If the universe turns out to be one of infinitely many, so be it. If it turns out to be the only one, that's fine too. Our job as scientists is to follow the evidence and the mathematics wherever they lead, even if they lead somewhere uncomfortable or incomprehensible. For you, as students, I hope this lesson expands your sense of possibility and deepens your appreciation for both what we know and what we don't know. Physics isn't a collection of settled facts to memorize. It's an ongoing conversation between curious humans and a mysterious universe, a conversation that regularly produces surprises. The multiverse might be the biggest surprise yet, or it might turn out to be a wrong turn in that conversation. Time and further research will tell. In the meantime, live your life as if this universe, this one you're in right now, matters. Because it does. Whether or not infinite other versions of you exist in infinite other universes, you only get to experience this one. Make it count. Ask questions. Challenge assumptions. Be open to impossible seeming ideas, but demand evidence. That's what science is all about. And if someday we discover definitive evidence that other universes exist, well, that will be absolutely extraordinary. And if we discover they don't, that the cosmos we observe is all there is, that's extraordinary too. Either way, we're living in an amazing time to study the universe. Thank you for your attention tonight. I know I've thrown a lot at you, from quantum mechanics to string theory to philosophical paradoxes about Boltzmann brains. If your brain hurts a little, that's a good sign. It means you're thinking about deep questions. Keep thinking about them. And remember, in at least one version of the multiverse, if the many worlds interpretation is correct, you just aced the exam on this material. Unfortunately, you're stuck in this universe, so you should probably still study. Good night, everyone. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.